Let's look at problem 5 from exam number 1 of a older exam from ECE 207. This particular problem says, suppose we have 3 capacitors in series. I'm just going to start drawing a picture so that I sort of know what I'm looking at. Those 3 capacitors are in series with a 100 ohm load resistor. So we're told what that resistance is. And they deliver an average pulse voltage equal to 1.9 volts. So we're looking at a pulse voltage of 1.9 volts, and they're telling us that the time length of that pulse is 0.1 milliseconds. And they want us to find the value of the third capacitor. Let's call this one C3. If we have known values for C1 and C2. C1, we're told, is 20 microfarads. C2 was 100 microfarads. And because of the series combination of those capacitors, if we need it, we know that the equivalent, or 1 over C equivalent, is just 1 over C1 plus 1 over C2 plus 1 over C3, so that C equivalent, if we need it, is now the reciprocal of this sum of reciprocals. And we know what this one is, and we know what C2 are equal to. This is 20 microfarads, and this is 100 microfarads. And we'll be able to then use that information if we can understand what the problem is asking relative to maybe an equivalent RC circuit. We now have something that looks more like, here is our equivalent capacitance. Here is our resistance 100, and now we're told what this voltage pulse looks like across this resistor, and we'll call it a load resistor. We now know that that's 1.9 volts on average, and this is 0.1 milliseconds in length of time, and this is voltage V sub L. Let's now figure out what we have. Well, if this pulse across V sub L is 1.9 volts for a particular length of time, and we know the resistance, we actually can find the current going through that resistor. Let's call it I sub L. That's just V sub L over R sub L, if this is now R sub L, and on average it's 1.9 volts. This was a 100 ohm resistor, and so we now have 0.019 amps for our current that's going through this series connection of a capacitor and a resistor. We also know this relationship between a capacitor and its capacitance, its charge, and its voltage. We know that Q is equal to CV. From that, if we differentiated and assumed that we had constant capacitance, we would have dQ dt is equal to C dV dt, and that's actually what gives us this formula that I'm always, or mnemonic that I'm always using, and that's ICE. So here's I, C, and E. There's ICE, and that's coming from Q is equal to CV when we differentiate that. But Q is equal to CV can be used right now. We know our change in voltage is 0.2 volts. That's the assume that the pulse voltage actually changes value by 0.2 volts. That was in our problem statement right here. And that tells us how much our delta Q is during this pulse. And so now we have this delta Q is equal to C delta V relative to this delta V being equal to 0.2 volts. And we know the capacitance. We don't know the capacitance. This is now our C equivalent, and we need to find that. But now, if we could find this delta Q, then we could solve for C equivalent, or have that value, and use that in this expression to solve for the only unknown if we do know C equivalent, and the only unknown would be C sub 3. Now we need to see if we can find a delta Q. But remember what the current, displacement current in a capacitor is. I is equal to just dq dt, or the change in charge per change in time. If we now solve that for delta Q, we now see that that's I delta T, and I now is the 0.019 amps that we had calculated before, and we know our length of time. So this is now 0.019 times our length of time, which is 0.1 times 10 to the minus 3, or let's just say that that's 10 to the minus 4. Or we now have 1 times 10 to the minus 6, or 1 microfarad, is the delta Q. This now value for delta Q can be used there, and now we have this C equivalent value that we can use. It's now delta Q over delta V. This was our delta Q has actually been miscalculated up here. I dropped the 0.9, so this is now 1.9, and this is not farads, this is in coulombs, so that's 1.9 microcoulombs, with this being our I, and this is our delta T. This is coulombs per second is I, and this is our seconds, so we now have coulombs of 1.9 micro. That now says that we have 1.9 times 10 to the minus 6. That's our delta Q over our delta V, which was 0.2. This now gives us 9.5 times 10 to the minus 6. And now, since this is capacitance, that's in farads. Or we now have, since C equivalent was equal to 1 over C1 plus 1 over C2 plus 1 over C sub 3, we know everything in that expression except for the C sub 3 value. Or we can now say that we have effectively then 9.5 times 10 to the minus 6, that was our C equivalent, is equal to 1 over 20 times 10 to the minus 6 plus 1 over 100 times 10 to the minus 6 plus 1 over C sub 3. And if we multiply by 1 over here, we can say that we now have 9.5 times 10 to the 6. Let's say this is now 100 times 10 to the minus 6 that we'll multiply by numerator and denominator in order to cancel or clean up some of this. That's now 5. This is 1. This is now plus 100 times 10 to the minus 6 over C sub 3. We now have 9.5. We can cancel some of the 10 to the minus 6's. And we have 9.5 times 6 plus 100 times 10 to the minus 6 over C sub 3 is equal to 100. We can divide out the 9.5 if we want to and subtract by 6, or we now have 100 times 10 to the minus 6 over C sub 3 is equal to 100 divided by 9.5 minus 6, or this is roughly 10 minus 6, but that's now 4.526. We then see that C sub 3 is equal to 100 times 10 to the minus 6 divided by this 4.526, or this becomes roughly 25 microfarads, but it's 22.1 times 10 to the minus 6 farads, or C is approximately 22 microfarads. And that's the the capacitance of C sub 3 when you have this charge pulse bled off from it, as stated in the problem.